Every time we look up at the night sky, we are looking back in time. The light from distant stars has traveled for thousands or even billions of years to reach us. But even then, we are only seeing part of the picture because there are two great barriers to our view. The first is swirling cosmic dust, which hides everything behind it. The second is the steady expansion of space itself, which stretches light beyond our visible spectrum and into the infrared. For centuries, these barriers have allowed the universe to keep its deepest secrets hidden. We've never seen the first galaxies or witnessed the earlier stages of stellar formation. But on Christmas Day 2021, all that changed. We finally launched the so-called Golden Eye that would allow us to lift these cosmic veils forever. The James Webb Space Telescope. A $10 billion, three-agency collaboration, Webb is the most powerful observatory ever constructed. Equipped with ultra-sensitive infrared detectors, it's not only able to peer through the dust, it can see even the faintest and most distant objects. This telescope has revolutionized how we see our universe. We've seen wonders close to home, auroras on Jupiter, and the iconic pillars of creation, and those further afield, gravitational shockwaves and galactic collisions, to name a few. But Webb wasn't just created to send back pretty pictures. As of 2025, it has already completed more than 860 scientific programs and collected nearly 550 terabytes of data. That's more data than Hubble accumulated in 35 years. These datasets are revealing a universe far stranger and more complex than we ever imagined. I'm McColgan, and you're watching Astrum. Join me today as we take a look at some of James Webb's most spectacular new images and unravel cosmic mysteries from across the depths of time. Becoming fully operational in July 2022, the James Webb Space Telescope was designed for one primary mission: to use its sensitive infrared detectors to pierce the cosmic dust clouds that permeate the universe, allowing us to observe the very first stars and galaxies. And it's off to a good start. Already some of its early findings are pushing the boundaries of what we thought we knew, challenging current models of how the universe has evolved. But to look that far back, James Webb has to peer through a lot of space. And along the way, it's made some remarkable discoveries around more familiar objects, ones that are only visible at infrared wavelengths. So let's take a trip across the cosmos and back through time, starting in our solar system and traveling to astonishingly distant early galaxies, all through the incredible eyes of Webb. Our first stop is in our own cosmic backyard, Neptune. Whilst it's usually easily recognizable thanks to its blue hue, with Webb it looks rather different. Doesn't it look ethereal? The methane in Neptune's atmosphere absorbs almost all of the infrared component of sunlight, meaning very little is reflected. There simply isn't much for the James Webb Space Telescope to pick up, making much of the planet appear dark. But this does have an upside. Instead, it allows the subtle, faint glow of Neptune's dusty rings and high-altitude clouds to stand out in dramatic detail. These are the clearest images we've ever taken. Not only beautiful, they've also revealed previously unseen ring arcs and shown us 14 of the ice giant's known moons. And this is just the start. Scientists are still poring over these images to uncover more of Neptune's secrets. I've already made a video on some of them if you want to find out more. But for now, the other secrets of the outer planets will have to wait, as Webb has been focusing its attention on one of the most compelling objects currently in our solar system, one that didn't start its life here. On the 6th of August 2025, Webb used its near-infrared spectrograph to join the fleet of telescopes and spacecraft observing the comet 3I Atlas. Its main focus was to analyze its composition. What Webb found has opened up a Pandora's box of possibilities. The comet turned out to be unusually rich in carbon dioxide and water vapor. In fact, the ratio was amongst the highest ever observed in any comet. It is a messenger from another star system, having formed in a region of its original star's planetary disk where temperatures were cold enough for CO2 ice to naturally freeze out. By directly sampling the comet, James Webb has proven that the basic building blocks of planetary systems and life are shared across the galaxy. The common elements and chemical processes that created our solar system are likely universal. But this extraordinary telescope hasn't just proven useful in exploring worlds in our cosmic backyard, it's also part of the hunt for new worlds beyond our star. And yet again, it's making some astonishing finds. The search for exoplanets is well underway. Thanks to missions like TESS, the Transiting Exoplanet Survey Satellite, and Hubble, we've already found more than 6,000 of them. But they've only been able to gather so much information. To find out more about these strange new worlds, they needed another instrument, and that came in the form of James Webb. It's found that our closest star has been keeping secrets. Just over 4 light-years away lies the Alpha Centauri system, a trio of stars that includes 2 Sun-like stars, Alpha Centauri A and B, and the red dwarf, Proxima Centauri. For decades, astronomers have suspected that planets might orbit the 2 Sun-like stars, but the immense, overlapping glare of the binary pair made them impossible to detect. Webb has overcome this obstacle, using its mid-infrared instrument and an internal chronograph to block the intense starlight. Much like you might use a car's visor to block direct sunlight so you can see on the road, this device stops the bright starlight and allows the faint light from the planets around it to be seen. This is an incredibly challenging observation, requiring meticulous image processing to subtract the residual light from both Alpha Centauri A and its companion star B. The resulting faint point of light, detected by MIRI, is now the closest ever exoplanet candidate to be directly imaged. It has given us strong evidence of a potential Saturn mass gas giant orbiting Alpha Centauri A. And even more surprisingly, based on orbital simulations, this gas giant likely follows an elliptical path within the star's habitable zone. While the gas giant itself would not likely host life as we know it, its existence confirms that a planetary system has formed around our nearest stellar neighbor, providing the potential for smaller, habitable moons or other terrestrial worlds yet to be discovered. Now, if planets and moons form throughout the universe, which we very much think is the case, the next question is, how? And this is once again something the James Webb Space Telescope can help answer. So let's continue our journey by diving into the immense, chaotic processes of creation. The cosmic cliffs, part of the Carina Nebula, 7,600 light-years away, and the iconic Pillars of Creation in the Eagle Nebula, 6,500 light-years away, may be familiar sights to some of you, thanks to the stunning visible light images captured by the Hubble Space Telescope. But Webb has given us an entirely different view. Rather than competing, Webb acts as Hubble's companion, using the infrared part of the light spectrum to peer through the thick, obscuring dust that Hubble's visible light can't penetrate. In this image of the Pillars of Creation, Webb's near-cam view reveals thousands of previously unseen stars, including newborns that were completely hidden within the dark, dusty columns in Hubble's images. They appear as bright red orbs lying outside one of the dusty pillars. Estimated to be just a few 100,000 years old, the red glow comes from energetic hydrogen molecules created in plasma jets and shock waves emanating from the new star within. It's as if the top of the pillar is pulsing with activity. Similar processes have also been seen as the cosmic cliffs. Here, Webb's NIRCam has captured crisp details of the turbulent gaseous structure at the edge of the nebula. This sharper look reveals that they are actively being sculpted and eroded by intense radiation from massive young stars just above them, a process much harder to visualize in Hubble's previous data. This new ability to peer inside these cosmic nurseries fundamentally changes our understanding of how stars and planets are born, finally allowing us to put theories based on simulations to the test. And what Webb is finding is that infant stars are not calm. Their births are explosive, energetic, and always spectacular. Deep in the outskirts of the Milky Way, in a region known as Sharpless 2284, approximately 15,000 light years away, our golden eye found something extraordinary. A true behemoth of a protostar, weighing as much as 10 times the mass of our Sun. But not only that, this massive star is unleashing huge jets of gas and radiation. Known as a bipolar outflow, they are created as superheated gas falls inward toward the protostar's core and then is simultaneously blasted back into space. Powerful magnetic fields channel this material into narrow, high-velocity jets launched outward at hundreds of kilometers per second. Spanning 8 light years, these spectacular birth announcement jets are nearly double the distance from our Sun to the Alpha Centauri system, and are immensely powerful, acting like a cosmic snowplow, pushing away the surrounding molecular cloud material and creating 2 much larger, opposing lobes of gas. This is a rare example of what's known as a hair-big Harrow object, bright patches of gas and dust that form when these jets collide with surrounding material. Although over 300 hair-big Harrow objects have been observed so far, these jets are particularly rare due to their immense size and strength. The stable, symmetrical nature of the outflow suggests the star is forming via an ordered disk, which provides crucial evidence for the core accretion model of massive star birth. What makes this discovery even more exciting is the fact that it's located in a star cluster on the far edge of the galaxy, where metallicity is extremely low. This means it has far fewer heavier elements than our Sun, and by heavier elements we mean anything beyond hydrogen and helium. This pristine environment almost perfectly mirrors the conditions of the early universe. By gazing through its infrared lens, Webb is giving scientists crucial clues to something that has long been a mystery: how the very first massive stars may have formed. But stellar birth isn't the only part of the creation process we don't fully understand. Planetary formation is equally mysterious, and yet again, something that James Webb Space Telescope is illuminating for us. Once a young star settles, the chaos around it begins to organize. The remaining swirling dust and gas becomes a protoplanetary disk, the birthplace of planets. As giant planets emerge within these disks, they can form miniature disks of their own. One example comes from the CT-Char b system, located 625 light-years away. This massive young exoplanet is encircled by a circumplanetary disk, a dense ring of material considered a moon assembly site. It's how we believe Jupiter's moon system formed long ago. Using its MIRI instrument, Webb delivered the first direct measurements of the chemical and physical properties of this potential moon-forming disk. Researchers discovered that the disk is carbon-rich, containing complex organic molecules like acetylene and benzene. This finding represents a major breakthrough, as this carbon-rich chemistry is in stark contrast to the disk surrounding the host star, where scientists detected water but virtually no carbon. This chemical difference, seen in a system that has only been evolving for 2 million years, allows us to compare the ingredients for forming moons in a distant system to the formation of our own solar system over 4 billion years ago. The universe is busy making worlds, and Webb is giving us an unprecedented front row seat. Now, we've seen how individual stars are born and how planets begin to take shape, but these stories don't happen in isolation. They play out across the vast, breathtaking structures of entire galaxies. In 2024, Webb focused on 19 nearby spiral galaxies, delivering images that are simply astounding. Forget the science for a moment and just look at them. If that isn't art, I don't know what is. You are looking at the heart of cosmic creation. In a galaxy like NGC 628, also known as the Phantom Galaxy or M74, located approximately 32 million light years away, Webb's view is special because it highlights specific galactic ingredients. The blue light marks millions of older, established stars clustered in the galaxy cores, but it's the incredible red and orange that demands attention. This is glowing dust and gas, nursery material that threads through the spiral arms like fiery motorways. The bright red areas are stars that haven't fully formed yet, still encased within their dusty peaks. You can also see that the spiral arms are filled with giant spherical shells or bubbles, massive holes carved out by the shock waves from ancient exploded stars. Analyzing these consistent patterns across 19 galaxies helps scientists understand how they build, maintain, and distribute the material necessary for stars, planets, and with that, life. But even now, with all this information, we still don't have the full picture. We have one step further to go. Instead of looking at fully formed old galaxies, we need to know how and when they began. For that, we need to go back much further, to the very first stars and galaxies. It's time to travel back to the cosmic dawn, some 13.5 billion years ago. Even with the James Webb Space Telescope, with all of its spectacular technical advances, there are limits to what light can show us. The earliest light in the universe was released when space first became transparent, just a few 100,000 years after the Big Bang. Beyond that point, the universe cannot be observed with light. But luckily, physics gives us ways to see further than we otherwise could. Gravitational lensing. We see this effect when a galaxy cluster like RxJ 2129, located 3.2 billion light years away, is in the James Webb's view. This cluster is so heavy that its gravity warps space-time, acting like a cosmic magnifying glass that bends and focuses the light from galaxies behind it. In 2023, Webb captured a distant supernova explosion behind RxJ 2129, but the telescope didn't just see it once. Its light was split, creating multiple images of the same event. Because the light from each image took a slightly different, magnified route around the cluster, the supernova appears as echoes across time. Analyzing the time delay between each one, or how much longer the light took along each path, allows astronomers to precisely measure vast cosmic distances. This data is critical for refining the expansion rate of the universe, also known as the Hubble constant. There's been some disagreement over this value in recent years. You can watch my video on it here. But who knows, maybe James Webb can help solve it with measurements like these. And so, we have arrived at the very edge of the observable universe, close to the dawn of time. Here, Webb's NIRCam and NIRSpec instruments, as part of the JADE survey, have pushed observation to its limit. The challenge is that light from the earliest galaxies is severely affected by the cosmological redshift phenomenon. This occurs because the expansion of the universe stretches light waves as they travel across vast distances of space, shifting the light from the visible spectrum all the way to the infrared, exactly the kind of light Webb is designed to capture. It has uncovered galaxies that existed far earlier and are far brighter than we expected, and one in particular stood out. Webb's near-spec instrument confirmed its redshift to be 14.32. This galaxy, now named Jade's GSZ-140, is seen as it existed only 300 million years after the Big Bang, making it one of the earliest known galaxies in the universe, beaten only by MOM-Z14, which James Webb also spotted in May 2025 and is 10 million years older. The prevailing lambda cold dark matter cosmological model predicts that galaxies at this epoch, often referred to as the cosmic dawn, should be small, dim, and only just beginning to form their first, simplest stars, which is almost the opposite of this new discovery. Jade's GSZ-140 is too mature, too soon. To grow a galaxy this large only 300 million years after the Big Bang, the early universe must have been forming stars far faster and more efficiently than any current model allows. The very existence of this galaxy and several other similar sources forces astronomers to confront the possibility that the foundations of modern cosmology need a serious revision. One explanation for this contradiction revisits a bold idea first proposed in 2007 by cosmologists Catherine Fries, Paolo Gondolo, and Douglas Spoiler: the existence of dark stars. These hypothetical first stars are not powered by nuclear fusion like our Sun, but by the gravitational annihilation of dark matter particles within their cores. These potential first stars could grow enormous, millions of times the mass of the Sun, cool, and be long-lived, producing the infrared light Webb specializes in. So we could be looking at the signatures of dark stars. This fundamentally connects the most distant observations to the least understood component of our universe. So yes, the James Webb Space Telescope has literally shed light on our universe in a whole new way. It has revealed a cosmos richer and more complex than we ever dared to imagine. I am super excited to see what James Webb finds next, and with potentially more than 20 years of functionality still on the clock, there's surely a lot more to come. Which of those images did you like best? Let me know in the comments what you want James Webb to look at next. Just past Jupiter, a comet has been randomly exploding for years, and no one knows why. These aren't cute little bursts. This is believed to be the most active comet in the solar system. We've seen it get nearly 300 times brighter in just a couple of hours, explode 4 times in 2 days without warning, and spew over 1 million tons of debris out faster than the speed of sound. And what makes it even stranger is there's no obvious trigger for the explosions. No dramatic swing into the sun, just a peculiar, icy body acting unlike anything we've ever studied. I'm Alex McColgan and you're watching Astrum. Join me today on a tour of everything we know about Centaur 29P and why we think it acts out so violently, and the recent discoveries of the James Webb Telescope that flip these assumptions on their head. In 1927, 2 astronomers at Hamburg Observatory, Arnold Schwarzmann and Arno Arthur Wachmann, discovered Centaur 29P while comparing a series of photographs of the night sky, initially classified as a short-period comet 29P was later reclassified as a Centaur, the name given to a group of small solar system bodies orbiting the Sun between Jupiter and Neptune. They exhibit characteristics of both comets and asteroids, much like mythical centaurs were half human, half horse. It's thought that centaurs originated in the Kuiper Belt, but eventually moved inward due to the subtle gravitational influences of the gas giants over the last few million years. Centaurs generally have elliptical and unstable orbits. Most will eventually be flung into the inner solar system as comets join the Jupiter family comets, or be catapulted out of the solar system entirely. Because of this, centaurs represent a short-lived transitional state in a small body's journey from the Kuiper Belt to the Jupiter family comets. We think Centaur 29P could be launched into the inner solar system as early as 2038, when a conjunction with Jupiter will change the path of its orbit. But Centaur 29P is different from most centaurs in two big ways that will be relevant later. Firstly, its orbit isn't elliptical. It traces an almost perfect circle around the Sun. And secondly, it is big. Measuring 60 kilometers in diameter, it is wider than 96% of all centaurs and is one of the largest known cometary bodies. Oh, and it explodes a lot. It's the second most active body in the solar system after Io, exploding on average about 30 times per year, and 40% of these strong outbursts don't happen in any kind of predictable fashion. These explosions are erratic, sudden, and very intense. Following an outburst, the comet reaches peak brightness in about 2 to 3 hours. In 2024, it made headlines when it erupted 4 times in a 48-hour period, appearing almost 300 times brighter than normal. 2 years earlier, it shot more than 1 million tons of debris into space faster than the speed of sound, like popping the cork out of the world's most pressurized champagne bottle. The main outburst then triggered 2 smaller ones 5 and 7 days later, which seems to be a common occurrence for the comet. And even though those sound incredibly violent and powerful, things get even bigger. In September 2021, Centaur 29P underwent the largest outburst in 40 years when it blew its top 5 times in a row. Despite the massive blast, it wasn't scientists who initially noticed, it was amateur astronomers. This is one of the curiosities of Centaur 29P's history. Most of its eruptions are first observed by hobbyist stargazers. It's easier to pull out your backyard telescope and get approval to point a multi-million-dollar public-funded instrument on your special interest randomly exploding centaur. When scientists heard what had happened, they managed to secure precious Hubble time to take a closer look, but the universe had other plans. As bad luck would have it, the day before the scheduled observation of Centaur 29P, Hubble experienced a technical glitch and couldn't be used. So, what causes these outbursts? How do we know about Centaur 29P's properties that could possibly explain them? If you suspect volcanoes, you're kind of right, but not the hot, fiery kind. They are ice volcanoes. Centaur 29P is what we call a cryovolcanic comet. These are generally covered in an icy shell with ice, dust, and gas inside, mainly carbon dioxide, carbon monoxide, and nitrogen gases in a frozen, icy state. Over time, radiation causes the crust to weaken from solid to gas. This forces internal pressure to rise. Eventually, it gets too much and the outer shell cracks, unleashing a visceral eruption of cryomagma from the inside of the comet, a mix of frozen water, ammonia, salts, and volatile gases like methane and nitrogen gas. See? Ice volcano. Centaur 29P's nucleus has a high escape velocity, and most debris isn't ejected fast enough to break free from its gravity. The result is most falls back onto the Centaur's surface to reform its crust. This may then trigger the knock-on outbursts 5 or so days later, as we saw in the 2021 outburst. Around the comet nucleus, the ejected dust and ice particles form a hazy, reflective cloud, lingering for days, up to a couple of weeks, making the comet look brighter, sometimes by several orders of magnitude. Some cryovolcanic comets like 12P, also known as the Devil Comet for the horn-like plumes that form during its outbursts, are on highly elliptical orbits around the Sun. As you might expect, the closer to the Sun they get, the more active and volatile their behavior becomes. But Centaur 29P is on a circular, not an elliptical orbit. It's always roughly the same distance from the Sun, so you'd expect a pretty even absorption of solar radiation and regular, predictable activity. However, as we've seen, that's not the case at all. So why are these eruptions so erratic when they shouldn't be? What's going on here? Scientists have been trying to work out if there is any method to the madness of the Centaur's eruptions for years. Some have speculated that the eruptions may be related to its slow rotation period of 57 days. More specifically, they observed that major outbursts were more likely to happen every 52 to 60 days, but smaller outburst events also occurred every 30 and every 90 days, with enough regularity to make scientists think that there might be some kind of seasonal cycle governing the comet. While Centaur 29P's eruptions seem to happen quasi-periodically, they are utterly unpredictable in terms of intensity or precise timing. That didn't stop astronomers from trying to anticipate when our feisty friend would blow. In April 2023, scientists noticed the light surrounding the comet's nucleus had become fainter than ever, suggesting a slowed rate of outgassing. They predicted pressure was building up inside the nucleus at a faster and faster rate, making an eruption highly likely. And just like that, Centaur 29P gave off a mini outburst later that very same day. It was the first successful prediction of an eruption on this weird and volatile little world. For the first time, we weren't just reacting to randomness, we got on the inside track. It felt like a breakthrough, and thanks to James Webb, we were about to have another. Until recently, we had never detected carbon dioxide on Centaur 29P. Carbon monoxide was always seen as the driver of these eruptions, mainly because it is consistently found in high amounts around the comet. But in 2024, data from the James Webb Space Telescope showed us that that was only half the answer. Data from the previous radio wavelength observations of Centaur 29P showed a carbon monoxide gas jet pointed towards Earth. But Webb's near-infrared spectrograph brought the jet's composition into greater focus, revealing not just one, but two jets of carbon monoxide, one pointing to Earth and one pointing towards the north. And that wasn't all. The James Webb Space Telescope also revealed two jets of carbon dioxide emanating from the north and south directions, the first definitive detection of the gas on the comet. The difference in abundance of carbon monoxide and dioxide suggests Centaur 29P might not be one object, but several objects that have become stuck together. The cause of the outgassing itself? Well, scientists still can't say for sure. But one interesting theory has been put forth to explain the unusually high carbon monoxide levels associated with Centaur 29P. Carbon monoxide is extremely volatile, and pure carbon monoxide ice can sublimate at temperatures as low as 25 Kelvin. If it were stored near the Centaur's surface, it would have all escaped a long time ago. So it must instead be trapped or preserved deep below the surface somehow. One possible solution is amorphous water ice. Almost all the ice we know of on Earth is in crystalline form. Crystalline ice is characterized by a structured, ordered arrangement of molecules. Amorphous ice, on the other hand, is not tightly packed. This makes it less dense than crystalline ice, and it also means it can hold gases within its structure. At temperatures above 77 Kelvin, amorphous ice turns spontaneously into crystalline ice. The higher the temperature, the faster this conversion occurs. In this process, trapped gases are released. So in theory, if Centaur 29P still has amorphous ice in its core along with trapped carbon monoxide, and that ice is undergoing conversion into crystalline form, then that could be where the high levels of carbon monoxide are coming from. How plausible is this theory? Let's break it down. Centaur 29P started in the Kuiper belt, with temperatures ranging from 30 to 40 Kelvin. At this temperature, all ice would be amorphous, since it only starts crystallizing above 77 Kelvin. As it traveled inward over 10 million years to its current location at 6 astronomical units from the Sun, temperatures rose to 115 Kelvin, and its amorphous ice started converting to crystalline ice. But how long will it take for all of its amorphous ice to turn crystalline? I mentioned earlier that Centaur 29P's size was going to play a role, remember? This is that part. First, researchers took 4 known small centaurs. They all measured between 1 and 6 kilometers across and were in a similar orbital position to Centaur 29P. They calculated that it would take those centaurs between 0.1 to 6 million years to convert their amorphous ice into crystalline ice. In other words, by the time they arrive in this position, they are already fully crystalline inside. All trapped gases released, no aces up their sleeves, predictable behavior. However, a centaur the size of 29P would take between 60 and 100 million years to convert all its amorphous ice. If these calculations are correct, it is possible the centaur has only converted 50 to 65% of its amorphous ice, and this has huge implications for its behavior. Converting lower density amorphous ice into higher density crystalline ice would shrink the overall volume of the nucleus. This could induce structural failures in the centaur's surface and interior. Some believe the subsequent cave-ins, landslides, and sinkhole creation events could be the driving forces behind the centaur's erratic outbursts. But regardless of the elegant explanation, another problem exists. Centaur 29P doesn't slowly leak gas. It erupts explosively, sometimes multiple times per year. How that pressure is able to build up fast enough to elicit several explosions back to back in quick succession is still not fully understood. Why Centaur 29P undergoes such bursts of brightness and how its outgassing actually works remain two of the biggest areas of investigation relating to this highly active cosmic body. It challenges our assumptions of just how fiery icy bodies can be in the outer solar system, and we still don't know as much about it as we'd like. But we've made progress. We're slowly starting to unravel its mysteries, and thanks to incredible tools like the James Webb Space Telescope, we're only going to keep learning. Picture this. It's the year 2500. The first probe to leave the Milky Way is finally passing our galaxy's outermost star. A historic moment that's being broadcast to every settled planet. The probe's name is Wanderlust 1. Its destination, our closest neighboring galaxy, Andromeda. But just as onlookers celebrate, something strange happens. Impact. Worlds watch in shock as the middle of the probe crumples in on itself, causing its metal to distort, buckle, tear, some vanishing entirely. The remains of the probe start spinning in space, its systems dead, And then the culprit becomes clear. Wanderlust 1 was hit by a primordial black hole. Of course, what I just told you is fiction, but tiny black holes with masses so small they are comparable to an adult rhino might not be. They could be out there, circling our galaxy's edges, and we may have just found proof that they actually exist. I'm Alex McColgan, and you're watching Astrum. Join with me as we delve into the darkness to solve the mysteries of primordial black holes. What are they? Where do they come from? And should we be worried? For a long time, tiny black holes, what I'm going to call black hole rhinos, seeing as they could have around the same mass, were thought to be impossible. Until the 1960s, we knew of exactly one way to make a black hole, and that was through stellar collapse. A star 20 times the mass of our sun or greater, running out of fuel and exploding in a supernova. All that exploded matter collapses, leaving behind an object so dense not even light could escape from its crushing gravity. This is a black hole. And because it formed from a star, it's a stellar black hole. But this isn't how all stars end. If their mass is less than 20 times that of the sun, it still goes supernova, but the collapse isn't quite powerful enough to create a black hole. Instead, we see a neutron star, a tiny celestial object that's still incredibly dense and made up almost entirely of neutrons. And for stars smaller than 8 stellar masses, they don't go supernova at all. So there is a limit to how big stellar black holes can be at birth. No larger than the largest stars, maybe a few hundred times the mass of our sun, and no smaller than a few times more massive. So why do we think that smaller than possible black holes could actually exist? Strangely, the answer is that we discovered bigger than possible ones. Today we know that at the heart of almost every large galaxy lies a gargantuan monster, a supermassive black hole. Back in the 60s, we were just beginning to discover these enormous beasts. The first quasar, a highly luminous and red-shifted galactic center, was found in 1963, kickstarting a roughly decade-long golden age of black hole research. The first predictions of a massive black hole at the center of a galaxy came in 1971. As the years passed and more evidence of these titans came to light, we realized they were mind-bogglingly massive, hundreds of thousands to billions of times the mass of our sun. But they are something of an enigma, and left scientists with one question in particular: how do they form? While it's technically possible that a stellar black hole could consume mass and eventually grow this big, this explanation started to break down as examples of supermassive black holes from earlier and earlier in the universe's history started showing up in our increasingly distant images of the cosmos. But for now at least, there wasn't a better explanation. Then came the James Webb Space Telescope. Launched on the 25th of December 2021 and switched on in 2022, it promised to see further and in better detail than any telescope had ever seen before. It would look for stars so distant, their light had started traveling at almost the dawn of the universe. And James Webb did not disappoint. These little red dots represent galaxies with supermassive black holes from just 500 million years after the Big Bang. Scientists realized this was not enough time for stellar black holes to grow to that size, not without devouring matter faster than the laws of physics should allow. Now, I've made a video on this idea before, and there is some evidence that this can happen, that black holes can disregard our speed limits on how fast they can eat to grow at rates we wouldn't initially have thought possible, that is, if we hadn't seen them doing it. But there are plenty of scientists who are skeptical of this answer, And there's an alternative theory, one that another recent James Webb discovery may have just confirmed as true. When it comes to forming a black hole, the key is density. When density is high enough, mass becomes so compact that its localized field of gravity passes a tipping point, and the speed at which you would have to move to get away from it becomes impossibly fast, i.e., you'd have to travel faster than the speed of light. The question is, how does matter get that dense in the first place? For that, you need a huge amount of energy, enough to overcome the electromagnetic force that stops electrons or protons from getting too close to each other. Then there's the neutron degeneracy pressure, a quantum mechanical force that says that two subatomic particles, two neutrons, can't occupy the same space at once. Neutron stars are not dense enough for their gravity to overcome this pressure, but they are still so dense that a spoonful of this matter would weigh as much as Mount Everest, over 900 billion kilograms. To make a black hole, you need forces able to crush the whole of Mount Everest into that teaspoon and then some. In fact, Mount Everest would have to be squashed into a space more than 1,000 times smaller than an atom to become a black hole. In the universe, as it exists today, such forces only exist in very specific circumstances, inside collapsing stars as they turn supernova. But go back in time, and that wasn't always so. Let's rewind to the earliest moments of the universe, within the first second after the Big Bang. There, those pressures did exist, albeit just for a moment. In this hot, dense particle soup, the distribution of matter was not completely homogeneous or evenly distributed. There were areas of high particle density and others where it was lower. Scientists believe it's possible that in particularly dense patches of space, black holes could have formed from primordial matter itself, skipping the star phase entirely. The result is called primordial black holes, and surprisingly, they aren't actually a new idea. They were first predicted in 1966 by Yakov Zeldovich and Igor Novikov. What's interesting about them is that they could have formed with masses 100,000 times greater than that of our Sun. This would be more than enough to account for the supermassive black holes that we see today, especially given the billions of years they've had to grow. Curiously, they didn't have to form as giants. They could also have been much smaller. A black hole the size of a single atom, with mass comparable to an asteroid, or a so-called black hole rhino that would be no bigger than a proton, but the mass of a rhinoceros. However, this was 13.8 billion years ago, and there are two problems with the theory that such tiny black holes exist today. The first is Hawking radiation, an extremely long wavelength of radiation that Stephen Hawking hypothesized black holes emit, gradually shrinking them over vast timeframes. It essentially tells us that, by now, all tiny black holes should have evaporated away. The second problem is that we haven't proven that primordial black holes actually existed in the first place. We've never seen a black hole arise out of the interstellar dust, or at least we hadn't until recently. In July 2025, NASA reported that the James Webb Space Telescope had seen two early disk galaxies, likely in the process of crashing into each other. But strangely, between them, and not in the center of a galaxy of its own, was a supermassive black hole. It had not somehow been ejected from either galaxy. They also have their own supermassive black holes, which left this third one completely inexplicable. The team who found it proposed that the black hole formed in situ via the direct collapse of a gas cloud. But this isn't the only evidence that black holes can simply appear given the right conditions. QS01 is a supermassive black hole that was also spotted by Webb. it inhabits a surprisingly small galaxy. Scientists were able to do spectral analysis and found that it's incredibly low in heavy metals, elements other than hydrogen and helium. This galaxy had less than 1% of the oxygen that we see in our own, and researchers called it one of the most chemically unevolved systems found in the early universe, which is telling. Stars usually produce these elements in just their first few generations, so the fact that they are absent in QS01's galaxy suggests that very little stellar formation has taken place yet, compelling evidence that wherever QS01 had come from, it had likely not been birthed by a star. Now, although not smoking guns, these two examples lend weight to the idea that the early universe was capable of producing primordial black holes. In fact, this finding may explain where all supermassive black holes came from. And if that's true, then it's almost certain that super tiny black holes used to exist too. But they're all gone, right? By now they should have dissolved. Well, according to one theory, perhaps not. Astronomy has a problem on its hands. As we track the amount of gravitational pull in the universe, it is much higher than it should be. Scientists conclude that there is additional matter inside galaxies, or circling them in large halos, something they've dubbed dark matter, because we can't see it. But you know what else carries serious mass and is quite hard to see? Black holes. Particularly ones with no accretion disks, because they formed directly out of interstellar matter. Of course, scientists have investigated this idea, and there's no evidence of large black holes surrounding the Milky Way, thankfully. If there were, stars would go flying like bowling pins every time one fell into our galaxy. We'd also see the light from stars behind them behaving strangely through the power of gravitational lensing, as the intense gravity of these black holes distorts the space around them. And we simply don't see anything that matches up to this. But tiny black holes, our black hole rhinos, would be very hard to detect through either means. There's no proof they're not there. The only argument is to say that they would have all dissolved by now. But this might not be the case. In April 2024, a study published in the monthly notices of the Royal Astronomical Society found that at tiny levels, Hawking radiation might slow down considerably, almost stopping entirely, which means these black holes might shrink and shrink until they eventually stop. Which, if true, means that black hole rhinos might be out there. Many believe dark matter circles our galaxy in a massive halo. What if, instead of all of that, it was tiny black hole rhinos? There could be millions and millions of them out there. A black hole minefield lying invisible and deadly. A swarm we could someday encounter if we ever attempted to leave the galaxy to explore another. We might be caged here without knowing it. Of course, space exploration has plenty of dangers all of its own, but it's more than unsettling to consider that as we voyage out into the dark, we could be on a collision course with a tiny, microscopic black hole with the mass of a rhino, or that one could be hurtling through space on its way towards us. Let's hope we find some evidence that this particular theory isn't true, or at least forget the idea of leaving the galaxy. I think I'd rather stay at home. You may have noticed this video didn't have any sponsors, and that's because it was brought to you by our astronauts on Patreon. Consider joining our Patreon to keep these videos thriving, even when they're sponsor-free. It's the reason we can research deep into the topics we love, without cutting corners or chasing clicks. Every new astronaut allows us to explore bigger ideas, and make every upload even better than the last. So if you've ever thought about being a bigger part of this channel, join the crew to power Astrum and keep space curiosity alive.